welcome. This is the ACIGS webinar series, and we're on webinar number 22 on the 18th of August 2022. The ACIGS is the Australasian chapter of the International Geosynthetic Society, and we are one of the 44 chapters globally, which encompasses 4,000 members, including corporate, individual, and student members. The ACIGS looks after the Australia, New Zealand, and Pacific Islands within our region. The International Geosynthetic Society, you can obtain more information by visiting their newly developed website. So you can see that at geosyntheticsociety.org, and within the IGS website, there are many resources available. There's information about the various committees within the IGS and how you can become involved. Current news and events from around the world. There's a digital library that includes lots of technical content. So there's Geosynthetics International and Geotextiles and Geomembranes journals available when you become a member of the IGS. There's a dedicated sustainability section with lots of current information, which are very useful to have a look at that. And the ACIGS, the Australasian chapter of the International Geosynthetic Society, we also have our own dedicated website. And within that, you can find out how to become either individual or corporate member of the ACIGS. We have a current and upcoming event section, so you can find out what events we have running. We've got current news for the region, and we have a dedicated resources section. So there's information for students. We've got information available for CQA and MQA. Documentation available, and we have a dedicated webinar library section. So all the previous webinars that we have run, you can access those and you can view those. So there's lots and lots of great content available there. So again, you can visit that at acigs.org, or you can use the QR code there in the bottom right hand corner. If you would like a certificate of attendance for today's webinar, all you have to do is just email info@acigs.org with your information and the webinars that you've attended, and we'll respond with a certificate that you can use for your records. And thank you to GPIL, Geosynthetic Partners International, for sponsoring today's webinar. These webinars can't go ahead without our sponsors, so thank you very much. And we've got Chris Barocos with us here today, and he will have a few words to share with us at the end of today's presentation. So thank you again, GPIL. So just by taking note of the headline news, we can all see how the current climate is not just affecting the Australasian region, but also globally. So today we're going to get an insight in how geosynthetic materials and design can contribute to the efforts of flood protection. So the title of today's webinar is Geosynthetic Barrier Systems Used for Flood Protection. And we're very lucky to be joined by Dr. George Kerner today from the Geosynthetic Institute. And I'm sure all our attendees know about George and the work he carries out. But here's a brief introduction. So George is the director of the Geosynthetic Institute.
Oh, Ryan, don't worry about that. Come on, here we go.
Okay. Well, I will leave it up for a second there, and we can digest that at a later stage. So thank you, George, and thank you for joining us from Georgia and Atlanta today. It's great to have you with us.
My pleasure. Great to be here. Thank you so much for the opportunity.
No problem. And any questions, if you could please post them in the Q&A section, and also include your name, because if there's any questions we can't get to at the end, we'll certainly be able to answer those and respond at a later stage. So be sure to include your name with any questions. So that's it for the introduction, and I will now pass over to you, George. So thank you very much.
Are you sharing me?
Yeah, you should be able to share your presentation now. Yep, that's good.
I hope you're seeing it.
Yeah.
Thank you so much. It's a pleasure to be here, and really, I wish I was in person. That's just about all I can say. I'll give you a little bit of background and definitions, but specifically, I'm talking about three topics: dams, dikes, and levees. And then I'll do some summary, recommendation, and conclusions. This is three sets of data, which you're seeing. This is sea level change over a period of 40 years. So we're seeing 12 inches or 30 centimeters of sea level change. And this is, again, three sets of data that show you this, and they corroborate one another. So this is troubling in and of itself. And that curve looks like it's increasing exponential. Who would be affected? I show you in the US, but then globally, anybody in red there is going to be affected. The incidents of extreme weather are in the news, as Ryan pointed out, and it's projected to increase over time. The Philadelphia metro area has experienced the 100-year storm 10 times in the last 6 years. So it's incredible. It's really, action needs to be taken, and action in regards to geosynthetics, I think, is on the horizon. First, a little bit about definitions of these three topics. Dams, man-made structures that run through a body of water. The purpose is to suppress floods, provide power, and a water supply. Dikes, on the other hand, are typically embankments with water on at least one side. This is to control flooding. These are structures to protect land that would be underwater anyway. Think of it as the Dutch sort of reclaiming land. Levees, on the other hand, are typically earthen embankments that are designed to control, divert, or contain water flow. So these are three distinct areas, and I'll hit these one by one through the presentation, and then give observations at the end of each of these sections. So first, about dam and dam waterproofing, and you'd be absolutely remiss if you were in this business and didn't consult this 2010 document by ICOL, which is the 135. It's a third edition, and it's like a phone book. It's sizable, and it summarizes 250 different dams around the world. Several are in the US, but most of the older ones are in Europe, and the newer ones are in Asia. Of those dams, the 250 of them, 213 have some sort of polymeric material, 21 bituminous, and then the others are sort of hybrid systems. They cover in these sections 7 different orientations, particularly with the membrane barriers on them. The geomembrane can be on the upstream side. Rarely it's in the core wall, but then you see the number and percentages of the total in this particular table. I have to give a shout out to Carpy here. I'll do it several times, but it really has led the way in this work. Please realize, going from the dam face, there's a needle punch non-woven, which acts as a protection layer, a cushioning layer, as well as a drainage layer, then the geomembrane, and then the water. So the membrane is the barrier system. The textile is a multi-component as a drain, as well as a puncture protection, and then the dam face itself. You can have several occurrences of this. This is a large vertical crack that you see in a concrete dam upstream. This is on the downstream side. So people with the landfill business, we are talking about different hydraulic heads here. These hydraulic heads are massive, and what that does is exert tremendous pressure on the geomembrane. So the membrane has to be much stronger and much more robust than for a surface impoundment or a landfill cover system. The systems look like this. They're quite stout and up to 5 millimeter thick geomembranes, which are placed. The thing that most people, or the general public, do not realize is that there's a drain or drainage composite behind that geomembrane. These membranes will leak. They will leak from the base as well as the abutments, but there will be leakage of seams as well. You have to accommodate that leakage. with the drainage material. So very important to have a composite system. The ICAL document is very detailed in the connection of the geomembrane and geocomposite to the concrete structure. They give actual details, and this is directly out of the book, so to speak, and it needs to be followed and followed well. The devil is certainly in the details with these connections, and certainly to learn from experience is paramount. Seepage control, there's going to be some leakage, and the amount of that leakage is due to the hydraulic head, but this is best predicted by experience. The amount of leakage in dams is very difficult to calculate. Like I said earlier, there'll be base and abutment sealing difficulties. A drainage system behind the geomembrane is always necessary. I don't know of any systems where it's geomembrane alone in any of those 7 categories. Either a thick needle punch non-woven or a drainage composite is required. The base composite often leads to an outlet structure where the amount of leakage is monitored over time. Composites also, and the drain also provides puncture protection for the geomembrane behind, but not in front of, and it's very important to have front protection as well. Not only are we retrofitting dams, existing dams, but we're building new panels or new dams in panel configurations with geomembrane associated with it. They're in the factory. They're typically precast panels which have a geomembrane attached to it, and then subsequently are seamed out in the field. This technique can also be done underwater. And I just have to give a shout out to Carby. They have a wonderful website which gives videos of this procedure being done. And it can be done with humans, which are supervising robotics. The technology has certainly advanced considerably over the last couple of years. A wonderful case history is from the late 90s out in California. This dam leaked since its construction. It was retrofitted, and 5 years after the retrofit, it's very nice to have the California Division of Safety of Dams make a comment like this, but this was really a wonderful experience, and they strongly recommend it and are using it going forward. In addition to those details with dams, we see geomembranes being used in inflatable dams. This is quite a stout material. It almost is the thickness of a tire and can be pneumatically inflated at critical times. I should say that it has a susceptibility for vandalism. We have too many guns in the US, so high-powered rifle will go through this, and at times like that, they're protecting these things, typically with stainless steel lift gates, so that the materials are protected over time. This gives the material protection from UV and also from vandalism. I don't know the situation in other countries, but FEMA is stockpiling inflatable dams throughout the country, particularly throughout the Southeast. This is for emergency disaster relief. The National Guard is equipped to do this and has training for it. We see it even in home ownership. So critical structures like pumping systems and electrical systems. New York City, for instance, has an entire sequence of these dams for all the subway systems and electrical conduits throughout the city. This is used also in civil engineering construction for coffer dams. The geomembrane is temporary, typically only in the neighborhood of 1 to 3 years. It has to have tremendous tensile reinforcement associated, so it's typically scrim reinforced material and used in conjunction with sheet piling or some sort of scaffolding system. As far as an overview for the dams, there's certainly trade secrets and patents associated with this. The installation details are very important, and the I-call document just touches the surfaces of this, especially when you're working in live situations. This is particularly critical. You need to focus on the connections, the joints, and the boundaries. That's the base as well as the two abutments, but the connections are extremely important, and to be done well and done correctly is usually a learned skill. There's quality control, quality assurance, and then operations and maintenance over time. One of the big things we're finding out is geomembranes on the face of the dam, particularly in cold weather, are seeing bombardment from ice movement as well as debris flows. So it has to be puncture resistant. There are systems, active systems, which are available for this, like bubblers. In addition to that, there are screens and nets which are placed over the around the water line to get away from the debris problems. Temporary dams are not generally reusable. From a sustainability perspective, this will probably change. This is a very big item going forward. I was just at a manufacturing facility that is recycling post-consumer scrim reinforced geomembranes, and it was quite an interesting study. It's neat how this technology is coming on. Moving on to the next sequence of dikes. These are typically submerged structures, and the biggest one that I know of is the Oosterschild in Holland. And I was very fortunate as a young man to attend the conference, and we took a tour of this awesome structure. Geotechnical engineers are kings over in Holland, so I really enjoyed that. This uses geosynthetics and particularly geotextiles in mass on the platforms for these piers. You can see the platform, which is actually rolled up on this drum, uses many geosynthetics, high strength grid, as well as a geotextile, and then geotextiles as filter systems. Installed in '84 and a tremendous success. They equate this Oosterschild as similar to the U.S. space program as amount of money outlay, and the Dutch think they got their money's worth on this. It has been challenged by many storms and survived very well. Unfortunately, that is not the purview of dikes that I wanted to show you. The vast majority of the dikes that we see are built of geotextile tubes. We have some founders on here. Chris Lawson is here. I have to give you a shout out. I'm certainly, I didn't know you'd be on, but if you need to ask questions, probably we'll have Chris answer them. The geotextile tubes are factory fabricated. They have multiple access points where you can introduce an infill. The infill is typically dredged in, whether it be a sand or silty material. Sand is typically used for erosion control, whereas fine grain materials and even sludges can be placed, but they have to be dewatered within the geotextile tube. Water under hydraulic pressure escapes from the geotextile, which is acting as a filter and a flexible form, and sort of has a dual function. Usually deployed on land, but can be done underwater with considerable difficulty and divers. It's a fascinating area, and certainly ever growing. It's not just a primary tube. They're typically anchor tubes associated with it and a scour apron. Please realize that there's a lot of water being discharged from these tubes, and it can present erosion problems associated with that. You don't want to undermine the foundation of this tube prior to placing it in use. Can have different stacking configurations, but beyond this, the geotextile, the diameter of the tubes has really expanded over time. This is early pictures from the Great Lakes region of the United States for coastal protection in regards. And this is one of the earliest installations on the New Jersey shore in Atlantic City. I was just down there 3 weeks ago checking out the tubes, and they've done very well, made it through 3 hurricane systems quite well. There are failures of tubes which are in challenging applications. Wave action is very detrimental, and also when the foundation is weak, the geotextile tube has to accommodate the weaknesses in these foundations, and it's not so easy. I couldn't help myself, but I had to get a slide from down under. Ryan was sort of chuckling with me pre discussion, and this is a reef formation with both polyethylene, or excuse me, polyester and polypropylene geotextile tubes associated with it. The big item for you is that you're going to be working with the dredge. The dredges are amazing pieces of equipment, going from very thin 200 millimeter diameter dredge pipes, and we've seen some as big as 3-4 meters across when they're moving big ocean. But you will have a smaller dredge, which is typically feeding a hopper. What do you know about the dredge? The only known is the volume to be removed. The unknowns in this are tremendous. It's everything else. Site logistics, type of soil, density. The soils might change. The debris inside the soil, depth of water, size of dredge, type of cutter, vacuum, pumping distance, types of tubes, dredging pressure. So there's a lot of experience from the field that's superimposed in this, and you probably don't want this to be your first rodeo when you're using a dredge with geotextile tubes. It is certainly a learned skill. There's considerable experience that is needed for this, both from a theoretical and an empirical evaluation. It applies to unbalanced side forces acting on one side of the tube, particularly in a coastal erosion protection application, as you see in this cross section. You again have to have that scour apron and the anchorage so you don't have a slope instability. Must consider both the soil and the hydrostatic pressures. Perhaps wave overtopping is important. The scour and anchor trenches are certainly important. You need to focus on a pre-study. There has been wave tank modeling associated with this, and seepage and stability of stacked tubes. This is work from, again, Australia. Sylvester's work back in 1990 supplied for what tensile strength do you need. Equations have been developed for a large-scale lab test responsible for a correlation here, and the following relationships are certainly available for the tubes. He has developed these nomographs, and Plarchik has made it into a nomographs. These are rarely used anymore, but they were the beginnings of tubes. What's used now are computer programs. The ones from the Lechinskys I really admire. It's GeoCops. It's based on a plane strain 2D behavior of these tubes. The geotextile is very thin and flexible with negligible weight. The tube fills with a slurry or a dredge. The hydrostatic pressure on the tube is exerted on the geotextile. There's no shear stress from the slurry on the fabric. It's assumed to be 0, and the cross sections are some are as follows. This is what the computer program generates out, and you're most interested in that H, that height. That height of the tube is typically how you get paid. So that is the factor which is certainly the most important, and how far that is above mean sea level. The tube in the example, the effect of T ultimate is very dependent on the pumping of the tube and its subsequent geometry. There was an excellent paper in Geoamericas by Marcus Wilke, and he describes this, the internal design of the geotextile tubes. And please realize when you scale up these tubes, you're going to have many different seaming configurations, and you're wondering about the stresses on those seams, which are the most critical and the weakest link in the tube situation. The filling diagrams he showed here in different stages, and then subsequently worked out the different stresses. On the next photo, you'll see a graph of tensile strength with this H/D factor corresponding to the lower figures. And you can see how that tensile strength changes with respect to time. As you go larger and larger in that H/D, the tensile strengths go up exponentially. So it's quite significant once you get to these extremely large tubes to have stronger and stronger textiles as well as stronger seams. Also, which are important are the fill port connections. There are actually holes which are incrementally placed along the geotextile tube. They're discretely centered so that you can get maximum fill associated with it. It depends very much on the fill and the fill operation. I know I'm going quick through a lot of material here, but in that Atlantic City site, you saw that there was a hopper over top of the filling port, which they could discharge the dredge into and then subsequently meter into the geotextile tube. The prefabricated boots are typically sewn into the main tube with reinforcement, so you don't have pressure or escape there. Sewing without a selvage in this weak location is often problematic, and you do get blowouts with this. Some ingenious work has been done with Tenkata, and they've developed these ports which can be placed in there. We do have a test method for that at GSI where we can get an idea of the strength. But certainly this is a system that works very well and is quite robust and has seen some massive pressures, especially when you go very high in tensile strength with the large diameter tubes. In addition to that, you would like to get an idea of how fast the material will dewater. I think we're at the point where we've stopped using the hanging bag test and gone exclusively to pillow tests like this. A fellow by the name of Tom Stevens really championed this work through ASTM, and Chris Timmons as well. The response that you have is the slurry head with respect to time. It's certainly dependent on the marriage between the geotextile in the tube and the infill that you're placing. You have a nice tool to define that. When you get to dredge materials that need to be flocculated or coagulated, you can use flocculants with them and get an idea of performance based on this pillow tube. Observations about dikes. Geosynthetics used in this application since 1967. So you have 55 years of experience with this material. It's certainly not a new kid on the block. A lot of good experience and long-term good performance with this. Long-term challenges and difficult access to maintenance. Design is certainly doable now with the boundary conditions, but unfortunately the boundary conditions are ever increasing. The severity of the storms and the performance of these materials are ever changed. Performance has been excellent. However, there's a little bit of durability issues. The durability issues could certainly be taken care of with synthetic turfs or GCCMs. We see a big push in this regard, particularly when you cannot mound soil over top of it into a very formal dike configuration. Also, turf reinforcement mats can be used as well. Hydraulic analysis and design and long-term stability are certainly fine. I'd like to see a bunch more case histories with monitoring associated with that. I think we'll see that in the future, and I reviewed a couple papers for the Rome conference that I think we'll see some of that in there. The next section, though, are levees. And boy, oh boy, are we doing a lot of work with this. The U.S. was struck with multiple hurricanes. Probably the most significant one was Hurricane Katrina, which made a direct hit on New Orleans. It happens to be Region 5 of the of the Corps of Engineers, and this is the magnitude of the storm. I have to give a shout out to Propex, now with Solmax, but they contributed a lot of this work, which you're going to see before you. The distress on a levee, you can see this here. It's typically on the back side of the levee, the breach of the levee. There's erosion associated with it and instability of the slope. These are the stages of the erosion, and please realize the water is eroding the backside of the levee, causing instability with respect to time. This is typically protected, particularly when you don't have a lot of room with a T-wall or an I-wall. We have seen some lightweight infills being placed inside of the core wall in the form of foam, which is encapsulated, or lightweight aggregate. We've also seen geogrid reinforcements used here. A big investigation at GSI was to see if the geogrid was providing a preferential pathway through the levee system, and it very much depends on the hydraulic heads, how long those heads are sustained, and what type of geogrid is matched with the soil. We did testing of this both in transmissivity and flex wall permeameter hydraulic conductivity. The results will be presented in the Rome conference with IGS. This idea of levee protection is truly slope instability. They're typically shallow failures, and you're looking at a factor of safety with resisting forces versus the driving forces. The resisting forces certainly could be soil friction, cohesion, mechanical methods like anchors. The things which are the driving forces are gravity, impact, hydrostatic, and seismic pressure. This work with ground anchors has certainly taken a big charge, and marrying ground anchors or soil nails with geosynthetics on the surface has come in very strong over the last 20 years. Original work was and patents were obtained by Bob Kerner in this regard with spider netting. There's me in an earlier day doing work in the late 70s, early 80s on this, but now it's really dwarfed. Everything is off patents to these cable anchors in multiple sizes. So you typically use this in conjunction with a high performance turf reinforcement mat. There are many patented systems out there now. I see it all over the world and used in big construction projects. Again, one of the biggest construction projects that I know of is around New Orleans for levee protection. This is the levee armoring design developed by the Corps of Engineers. The type of levee is a hurricane production. This is for coastal protection. The storm surge in the neighborhood of 30 feet or 10 meters. And you see the different design criteria below. The levee armoring design, the design life is greater than 50 years. It not only will have a high performance TRM on it, but it will have a grass layer on it as well. The environment that this levee is in is both fresh and salt water, so it'll have brackish water on it. There will be some levee maintenance with grass mowing over top of it, and construction will be typically in lifts, and they will have to repair. So this system will have to have O&M associated with it. In that regard, the Corps of Engineers set out a big trial on this. There are a lot of this armoring to be done. And what I'd like to do is compare their best three options. Their three options were roller compacted concrete, articulated concrete blocks, and then high performance TRMs. So I'd like to go through a comparison of these three different alternatives and even take you into some sustainability considerations for this. To do this, we made use of work at Ohio State. They have massive flumes, full-scale overtopping. This can be accommodated with a massive wave associated with it. First was roller compacted concrete, which was placed at the end of this flume for the experiment. The next was the articulated concrete blocks, and it was more complicated for the high performance TRM because you had to grow vegetation on it. So they made the structure and then subsequently grew grass on this over a period of time and then placed it inside the flume for testing. You see the sections of this and the massive amount of water which was mobilized over top of it. To show you a comparison of this material, you would like to see first the comparison of the carbon footprint of this. This work was a combination of the US EPA plus the RAP report, which is quite famous in the UK, which it was the first I saw it. As far as the assumptions are concerned, you see the comparison of the roller compacted concrete, the articulated concrete mat, and the high performance TRM. The assumptions are written out or spelled out here. It's a little bit too detailed for this, but it gives you an idea of the level of comparison. In the sustainability comparison, it was no comparison at the end. The roller compacted concrete and the articulated concrete blocks were about equal as far as the amount of CO2. And then almost 2 orders of magnitude different was the high performance TRM. So this, as usual, the geosynthetic components present an extremely nice picture from a sustainability perspective. To summarize the entire thing is this table of the tons of CO2 emitted per square yard. And again, the comparison of the roller compacted concrete, articulated concrete block, and high performance TRM. You see the totals here, which really dwarf its material alone, delivery alone, and then the subsequent totals. As far as the money is concerned, it is also a big winner for HPTRMs in that regard, and this table sort of captures that. So now let's go and look at what the Corps of Engineers at New Orleans decided after all this work. So here you see a levee. First, the anchor trench is dug at the top. Subsequently, the slope is prepared, and then the anchor trench at the bottom. The high performance TRM is slipped in and overlapped correctly down gradient, and then subsequently the nails are placed, or the anchors are placed in prescribed sections which they hold. Following that, the Bermuda grass is planted over top, and this gives a very attractive system. They went big here with this. They armed the entire section. Here you see it, and you see New Orleans in the background. This is what they're protecting. They're protecting a bunch of different pumps from Lake Pontchartrain, but they are protecting most of the wards in New Orleans. How much do you say? 129 kilometers of levees have been protected in this regard. So they believe in this, and it has taken at least not a direct hit from a hurricane, but has fared quite well. And they're using more of it down in the core in the New Orleans district. Applications limits are the geosynthetic durability. Can the rod or anchor be driven to mobilize the strength in the geosynthetic is often asked. Are these resistant calculations reasonable? Can the surface be properly graded? Will the surface geosynthetics be robust enough? So we've been challenged with these questions, and GSI has really been working on a bunch of these, trying to get answers. The first one is in regards to the anchors, and you have a litany of different anchors that are available to you. These anchors are typically driven, and then they require a little mobilization to flip the anchor into action before it gives a resistance to the system. These are driven rods or anchors, which you showed. GSI has developed a test method, which is off of a load frame and a hydraulic ram. We can test these anchors in the field, and you get a load deflection plot. You see that load deflection plot in the typical anchors here, a little something to get it started, movement, and then subsequently, the pullout. You're not allowed to use the entire maximum. What you typically use is 2/3 of the elastic region for this. I used to work for Schnabel Foundation as a geotechnical engineer back in the day before my geosynthetic times, and that has always been the design criteria for the anchors. The next side of it, you need to know, do you mobilize the connection? And again, GSI has developed a new test procedure for this. It's GSI 29. We have two continuous rate of extension machines that work simultaneously at the same speed with a drum over top. We can do this with soil or in geosynthetic alone. You see my colleague Grace Swan, who just came back from Hong Kong today, I'm told. So I had to welcome her home. And you see three different types of failures. You see failures of the connection. You see failures of the cable, and you see failures of the geosynthetic. So these are the different types of failures that you see. This is a cable connection failure, a failure of the connector, and then a failure of the geosynthetic. The typical response curve is this, what you see. And again, this is different in isolation versus with soil. And certainly you need a good marriage between the geosynthetic and the connectors. But now you have a test method that'll give you this answer reliably. Another big section of this is when a levee is breached, can you use a geosynthetic to block the levee so that you can basically the finger in the dike, so to speak. This is done with geotextile tubes. The biggest finding from this is don't fill up the tube totally with water. Only fill it up in the neighborhood of 2/3 to 3/4 full. The rest of it will be open with air, and that subsequently works the best. You can release these sausages, so to speak, off of a barge. They have successfully gone after a 3-meter opening. Once it gets much bigger than that, though, it certainly gets problematic. So observations about levees, rehabilitation utilizing many forms of ground modification certainly is out there. The projects are certainly large and plentiful. They're talking about Miami, big projects in this regard, as well as all up and down the Northeast coast. It's innovative area and certainly fascinating. Geosynthetics is just starting in this. It really could be quite a windfall for all of us in this technical community. Design criteria are ever increasing in this regard, and certainly there'll be challenges going forward. As far as a summary of this presentation, it certainly has focused on flood protection. The applications are exposed geosynthetics in whole or in part, and this will provide challenges in regards to the formulation of these materials. It's a very different lifetime of a material based on full oxygen exposure of 21%, high temperatures, and also UV. Recommendations, predictable performance is the quest. You have both field and laboratory tests. Field performance is heavily dependent on site-specific conditions, seasonal change, and operation and maintenance. As far as conclusions, geosynthetics are indeed bona fide engineered materials. They work very well, but they're tricky. And we have to acknowledge this and work together to certainly get any of the mystery out of this and make them usable for people across the board. These are challenges that I certainly know that we can meet, and it's a great opportunity for all of us. Thank you so much. It's really a privilege to be with you, and I told Ryan I would not run over, so I've given you 15 minutes for Q&A. So I've kept my word, at least. It was quick.
Thank you very much. It's fantastic, and lots of useful content. And as you can see, there's plenty of geosynthetic types and designs that can be used, and lots of applications. So I'm sure it'll continue to grow, as you say. There's still a lot that can be done. One question that we have here. So what is the maximum recommended flow velocity for TRMs as levee hydraulic erosion protection?
I think that table that I gave you, I don't know it offhand there, but you know, the upper bounds of it are shown in that table. I can get that value to you. I don't know offhand, to be quite honest with you, but there's a very nice table by Mark Tyson, who shows them superimposed on one another. And whoever asked the question, I certainly will send them that table to give you the maximum. When I say that, though, there are quite a bunch of designs coming. The real trick is the resiliency of the material to make it three-dimensional, and also to have root growth through it. So it works in combination. And I'll give you two different tables, one vegetated and one non-vegetated in that response. I don't know it offhand, to be honest with you.
That's great. Thank you very much. We've got a few more minutes for Q&A if anybody else has got any questions. Okay, so question here, would it be possible to know the typical maintenance of the geotube, especially for slurry, after the shelf life, or do we just dispose of them and construct a new one?
Very different polypropylene versus polyester. I see almost all the tubes going to polypropylene now, very few polyester tubes anymore for the abrasion, except for certain applications. The polypropylene is loaded with a huge AO package, as well as it's a very thick fibrillated yarn. It has great UV. To stabilize it even further, I've seen it hit with a polyurea, a bitumen, or and the bitumen I don't recommend because of the hydrocarbon in it, or a latex. But both the latex and polyurea have to be sprayed, applied in the dry. They don't like the wet very much. So that has to be done as a preamble. Obviously, you could place soil over top of it and get it away, but those are your three areas of attack. One, making a nice formulation. Two, coating it with a spray applied material. Three, putting a permanent cover. And certainly the GCCMs or turf or HPTRM could be placed over top of it for to cover it or shade it.
Yeah, thank you. Another one here. So GRI GS29, the connection test for pull-out failure of geosynthetics. Is it suitable for geomembranes?
Oh, certainly. We've actually done that. The scrim reinforced membranes for exposed geomembrane covers. So yes is the answer. The tricky part is, and Ryan, I see you smiling, but you turn it upside down and you pull it against soil. It's a real bear to run in the laboratory. I hope Warren gets that down, and you know, so he can do that instead of me, because that's a monster to run that rascal.
All right,
but
great.
Yes is the answer.
Fantastic. Okay.
They're different anchor manufacturers, and boy, do they perform differently. I was just in the UK, and Duckbill has one, which is like a stainless steel plate. It looks like a flying saucer, but this thing is equipped to transfer tremendous loads. They could really use monster geosynthetics. So it's neat to see where it's going.
Yeah, great. All right, well, that concludes the questions that we have. If any more come through, I'll be sure to pass them along and get a response on that. But Chris had something today, so sponsor GPIL, Chris Brockles. I'll just pass over to you to end today's presentation. If you'd like to take over.
What's happening here? Okay, thank you very much. Thanks, Ryan. And thank you, George. That was a wonderful presentation. I think very stimulating, showing the history of where these tubes and variations on the tubes have come from. As you say, 55 years of R&D and development. It's not something that's new, but as with many things in the geosynthetic industry, we're seeing improvements all the time. Special thanks to ASIGS for giving me the opportunity to have a few words. Unlike most of the past presentations, I won't be doing a case study or any sort of presentation. I'd just like to touch on the fundamental reasons why, following the Australia-New Zealand conference in Brisbane just a few months ago, I made a decision to have my business, Geosynthetic Partners International, come on board as a corporate member. Primary reason is to not that we operate across both continents or both countries in the region fully, but I've been very inspired by what I've seen coming out of ASIGS in the last couple of years, and I think the organisation has matured a lot, which is wonderful to see. The conference itself in Brisbane was excellent. And by bringing GPIL into the corporate arena for ASIGS, I'd like to work with the existing individual members and corporates in the New Zealand scene to encourage increased participation in ASIGS by consulting engineers, central and local government organisations, relevant organisations, and the major contractors. I think it's these days geosynthetics have a lot to offer engineering construction, as we already know that those of us have played in the game for a long time. And I'd like to be proactive, working with Jonathan, the likes of Gordon Stevens and others, to encourage New Zealand participation in ASIGS. I think there's a lot to be gained, a lot of knowledge that can be gained for the New Zealand industry, construction industry. So that's all I really wanted to touch base on. Again, just to thank George for his very interesting and stimulating presentation. So thanks, George, and look forward to catching up with you in due course.
See you.
Thanks, Chris. Yeah, and thanks, George. Thanks for joining us late in the evening over there. It's very much appreciated.
No, I like that the technology worked, but I'd much rather be in person. So
all right.
have you. Okay.
Fantastic.
All right.
Take care now. Bye-bye.